Hello, my name is Brandi Everett, and today I will be presenting my final project for ADTA 5340. This presentation covers a comprehensive journey through machine learning, starting with a strategic proposal for United Healthcare and moving through 5 distinct technical exercises involving data preprocessing, model building, and evaluation using Python and Jupyter notebooks. Let's get started. We will begin by looking at the practical application of machine learning in a corporate setting, specifically United Healthcare. Then we will transition into the technical components of the project. We will look at data cleaning techniques and then evaluate the performance of several models, including k-nearest neighbors, random forest, decision trees, and linear regression across differing data sets. We will conclude with a comparison of these models and final thoughts on the importance of data quality. In part 1, I developed a strategy for United Healthcare, who manages millions of claims monthly and faces competitive pressure to reduce costs and improve efficiency. The proposed strategy leverages predictive analytics to address 2 key objectives: improving operational efficiency in claims processing and supporting AI-assisted patient risk scoring. By automating these tasks, United Healthcare can move faster on critical data insights. Before we discuss the specific machine learning strategy that will be deployed for this particular part of the project, it's crucial to understand the scale of the organization we are analyzing. As outlined in the project's company summary, United Healthcare is a massive entity generating approximately $330 billion in revenue annually. This scale presents a unique data challenge. United Healthcare processes millions of claims every single month. We are not just competing against rising costs, we are also competing against major players in the industry like Cigna and CVS Health, who are already deploying AI models. This massive volume of data makes United Healthcare the perfect candidate for the big data discovery methods we are proposing today. To achieve these goals, I proposed a multi-model approach. For operational efficiency, we utilize decision trees to classify incoming claims as either high risk, routine, or ones that need manual review. Simultaneously, k-nearest neighbor models are developed to detect anomalies that may indicate fraud. On the clinical side of the house, we will utilize regression analysis to calculate patient risk scores based on variables like BMI, lab values, and chronic conditions. Patients who score above a 0.8 in the model would automatically be flagged for preventative care and nurse outreach. To execute this strategy, we need a robust technology stack. The entire project is built on a Python ecosystem. We utilize Jupyter notebooks for the development phase, allowing for iterative testing. The heavy lifting is done by scikit-learn for the modeling and pandas for the data manipulation. Crucially, the end goal is to deploy these models via API endpoints, allowing the claims processing dashboard to query the model in real time. This is not just a one-off project. It is a 3-year transformation. I expect full integration within a 3-year timeframe. We'll start by piloting the claims classification models to build trust, and by year 3, we aim to have a scalable framework that automates the majority of routine tasks, resulting in measurable cost savings and improved member outcomes. The expected return on investment for this strategy is significant. Within 3 years, we anticipate a 30 to 50% reduction in claims processing time and an increase in fraud detection capability to approximately 80%. Clinically, by accurately identifying those high-risk patients, we aim to reduce hospital readmission rates by 15%, ultimately driving down costs and improving member health. A win-win if you ask me. Moving to part 2, we'll focus on data preprocessing using the Austin Animal Shelter database. The first challenge we encountered was that the raw CSV file completely lacked column headers. Using pandas, we had to manually map the columns to meaningful names like animal ID, intake date, and outcome type. This step was critical because without proper labeling, any subsequent analysis would be meaningless. Initially, every single column was read as categorical text object, which required significant transformation. Once our headers were assigned, we acted as detectives to find missing data. I identified gaps in 3 key variables: sex upon outcome, age upon outcome, and outcome type. We ran a unique value check and confirmed that the missing entries were already coded as NaN by the system, meaning that we didn't have to replace obscure placeholders like question marks or zeros at this specific stage of our analysis. Our transformation design focused on converting qualitative text into quantitative signals. The original dataset was entirely categorical. A model cannot understand the text 1 month versus 2 years. I designed a transformation step to convert these strings into numerical values. I also engineered a new feature by converting date of birth into age in years, providing a continuous variable that correlates strongly with adoption rates. The final result of part 2 was a streamlined numeric dataset. We stripped away administrative noise, specifically the animal ID and name columns. As noted in the report that will be turned in with this assignment, an identifier like animal ID has no predictive meaning for an animal's outcome. The final output was saved and downloaded, marking the successful conclusion of the pre-processing phase. We now have a clean foundation to start building predictive models. I want to make an important distinction here. In this section we just covered in part 2, I did not run a machine learning model or generate accuracy results. This part of the project was exclusively dedicated to the data preprocessing phase, which is the prerequisite for any modeling. Now that we understand how to clean data, we will transform it in part 3, where we will apply these principles to the abalone dataset and build our first actual predictive model for this project. In part 3, we use the abalone dataset. We're dealing with various physical distributions in this particular dataset. And K nearest neighbors was selected as the algorithm that we would evaluate this data with because the relationship between physical size and age is nonlinear. A linear model would struggle here, but KNN works well by looking at the neighbors or similar instances to predict the age of new abalones. Let's discuss the results. we achieved a test accuracy of only 23.3%. While this seems low, it's important to understand why. The data has many different ring counts, and some of those ring counts have very few samples. This makes it difficult for the model to learn those specific classes. Essentially, it's trying to predict the exact number of rings, which is hard in a classification problem. Future iterations of this model would likely benefit from grouping these ages into broader categories. Despite the low overall accuracy, the model did demonstrate logical consistency when we fed it new records. If you look at the table here, we have record 1, a small abalone with a length of 0.35. The model predicted an age of 7.5 years. Contrast that with record 2, a much larger abalone with a length of 0.62. The model predicted 10.5 years. This confirms that the KNN algorithm is correctly identifying that larger physical dimensions correlate with an increased age. We need to discuss why the abalone model underperformed and how we would fix it in a real-world scenario. Our results highlight that treating age as a specific integer, like predicting exactly 9 rings versus 10, is incredibly difficult due to the overlap in physical traits. My recommendation for future iterations would be to move to binning. If we grouped the abalones into young, adult, and old, our accuracy would likely skyrocket as the model could more easily distinguish between those broader categories. Moving on to part 4, we utilize the adult salary dataset to predict if an individual earns more or less than $50,000. For this model, I chose Random Forest for this task. Random Forest is excellent here because it handles the mix of demographic, our categorical variables, and financial, our numerical data, very well. It also generally avoids overfitting better than a single decision tree by averaging predictions across multiple trees. However, this section provided a critical lesson in data quality for me. If you look at the table on the screen, notice that we have classes 0, 1, 2, and 3. This, however, should be a binary problem, just 0 and 1. So what happened? The target variable had inconsistent formatting. Some entries had a trailing period, like less than 50K dot, while others did not. This caused the computer to see 4 different income groups instead of only 2, which ultimately dragged our accuracy down to 52%. This specific example really proves that preprocessing is the most vital step in machine learning, and one that I caught after the model was built. Despite the classification error, however, we ran predictions on 2 new records shown here in this table. Record 1 represents a younger individual with an age of 28 and with 0 capital gain. The model predicted an income of less than 50,000. On the other hand, record 2 represents an older individual with an age of 47 and significant capital gain of over $7,000. This model predicted an outcome greater than 50,000, which aligns with our feature importance analysis, which showed that capital gain and age were major drivers for the model's decisions. Beyond just predicting income, the random forest model gave us insights into what predicts income. Feature importance analysis revealed that capital gain was the strongest predictor, which makes logical sense as investment income pushes total income up. Education level and hours worked per week were the next most critical factors. This confirms the model isn't just guessing, it's identifying real socioeconomic drivers in our data. We identified the data error where periods were creating duplicate classes. In a real-world project, identifying the bug is only half the battle. Fixing it is the other half. On this slide, you'll see the exact Python code that I recommend to solve this. By using a string replace function to strip the trailing periods before the model training stage, we would consolidate our 4 classes back into only 2 like we expected, which would likely double our accuracy and fix the confusion matrix. In part 5, we analyzed the car evaluation dataset. This time, we achieved a massive success, utilizing a decision tree classifier because it handles categorical and numeric data effectively. We had to perform some specific cleaning, such as changing the text value of 5 more for doors into the number 5. This allowed the model to process the data numerically. Please take a moment to look at the decision tree visualization that's on the screen. One of the greatest strengths of this algorithm is its transparency. Unlike a black box model, we can trace exactly how the model makes a decision based on the different variables. So for example, safety, maintenance costs, buying price, and it splits the data until it reaches a leaf node for the final classification. The performance here was outstanding, with a test accuracy of 97%. In the table on the screen, we see that the power of this model. We introduced 2 new records. Record 1, which contained 4 doors, was classified as very good. Record 2, on the other hand, despite having similar safety ratings, had fewer doors and different attributes, leading to an unacceptable rating. The model, through this, generalizes extremely well to new data, as seen in our predictions and our accuracy and cross-validation rates. Part 6, we had to go find our own data set, and for this particular one, I chose the white wine data set. This data set is a publicly available data set from the UCI Machine Learning Repository, and it is often used for regression and classification tasks in wine quality analysis. It contains the physiochemical properties of white wines and contains a quality score for each wine. It will be used in this project to predict wine quality based on these features. We initially treated this as a regression problem to predict exact quality scores using those physiochemical properties like acidity and sugar. We compared that with a linear regression model against a decision tree regressor to see which would better predict the specific numerical quality of the wine. Let's look strictly at the numbers on this slide. We used R-squared to measure goodness of fit. The linear regression model achieved an R-squared value of 0.269, meaning it explained about 27% of the variance in wine quality. The decision tree, however, failed completely with an R squared of only 0.022. This tells us that the decision tree was likely overfitting the training data and couldn't generalize, making the linear regression the clear winner for this specific task. I would like to take a brief minute to explain the R squared metric that we used here. An R squared result of 0.269 for the linear regression model means that our chemical data explains about 27% of what makes a wine good or bad. While this is statistically significant, it does leave the 73% of the quality unexplained, likely due to factors not in our data set, like brand reputation or age. The decision tree score of 0.02 essentially means it learned nothing useful about the general population of the wines, likely because it memorized the training data way too closely. However, linear regression has a major flaw: sensitivity to outliers. When we tested record 1, which had very high sulfur dioxide levels, the model predicted a quality score of 12.7. And since the scale only goes up to 10, it's an impossible value. The model saw the high sulfur numbers and extrapolated a trend line way past the logical limit. This is a key risk when using linear regression on data with extreme outliers. Because predicting the exact number was so difficult, we reframed the problem, and I went a little further beyond what was required and converted the target variable into 3 categories: low, medium, and high quality. When we applied a decision tree classifier to these bins, accuracy jumped to 73.1%. This demonstrates that while the data may not support precise numerical prediction, it does contain strong patterns for a broader categorization. Finally, in part 7, we compared linear regression against a K&N classifier for the wine data. The linear model gave us continuous predictions, but continued to remain weak. The K&N model, operating on our quality bins, achieved a cross-validation accuracy of 72.3%. The conclusion here is about the objective. If we need to know if a wine is simply good or bad, K&N is the preferred choice. If we need specific numeric values, we need to stick with a regression, but require more robust data or tuning. This brings us to the final strategic trade-off. Which model should we choose? If the business objective is to simply categorize wines as high or low quality, the K&N classifier is the preferred choice due to its superior accuracy of over 72%. However, if the business demands a specific numeric score, we need to use linear regression, but we must implement guardrails to catch impossible predictions like the 12.7 score we saw earlier. In conclusion, this project demonstrated the dual approach of strategic planning and technical execution. We showed how United Healthcare could save millions through automation. On the technical side, we learned that data quality is the single most important factor, as seen in the adult salary dataset, and that reframing a regression problem as a classification can significantly improve model utility. These frameworks are scalable and ready for future application. Thank you so much for your time today.